Today I'm going to discuss about the topic crystal field stabilization energy. So before going to this actual topic, so we need to see the factors affecting crystal field splitting. Since we have discussed different d-orbital splitting in different geometries, so one question arises is whether in all those geometries the magnitude of crystal field splitting will remain same, or is there any factors which will affect that magnitude of crystal field splitting. So before going to this crystal field stabilization energy, we need to see the factors which will affect the crystal field splitting. So the crystal field splitting factors, there are several factors. So some important factors which will affect the crystal field splitting we need to discuss. So the factors which will affect the crystal field splitting is as follows. So for the simplification, I have taken metal factors and ligand factors. So if you come for the metal factor which will affect the crystal field splitting is oxidation state, number of d-electrons, nature of metal and spin pairing energy. So if you come for the ligand factors, so we need to see the ligand character and number and geometry of the ligands. So these are the important factors which will affect metal d-orbital splitting. So we will see one by one. So first I will take oxidation state, how it is going to affect the crystal field splitting. So if you come for the oxidation state of the metal, higher the oxidation state of the metal ion causes the ligands to approach more closely to it, and therefore the ligand causes more splitting of metal d-orbitals. So if the metal is in higher oxidation state, then the size will become smaller and its tendency to attract the ligands will increase. So thereby the ligands will approach closer. So since it is an electrostatic force of attraction, so metal charge increases means its capacity of attracting the ligands towards itself will increase, and thereby the splitting of d-orbitals will take place in the case of metal which is having higher oxidation state. So I have taken two examples, hexa, aqua, cobalt. Here the cobalt is in +2 state and its crystal field stabilization energy will be 9200 per centimeter. So same complex, aqua complex, but here the metal will be in +3 oxidation state. Then you see the crystal field stabilization energy, it has increased. So diagrammatically it can be represented like this. So since I have taken octahedral complex, so it will split into T2G and EG. Already we know how the d-orbital will split in octahedral complex. So this is in the case of +2 oxidation state, and if you see the case in +3 oxidation state, there is greater splitting. So this is the case. So whenever there is oxidation state is increased, obviously the crystal field splitting also increases. This is a direct relation. Higher the oxidation state, greater will be the splitting. So if we come for next, how the number of d-electrons will going to affect the crystal field splitting. So if you come for the number of d-electrons for a given series of transition metals, complexes having metal cation with same oxidation state but with different number of electrons in d-orbitals, the magnitude of crystal field splitting decreases with increase in the number of d-electrons. What is this meaning is, so if you are not able to distinguish between crystal field splitting since they are having same oxidation state. Suppose if I take the example of cobalt and nickel, here cobalt and nickel both of them are present in +2 oxidation state. Then how we are going to decide? Because already we have discussed oxidation state, it is directly related to crystal field splitting. But now the scenario is different because here the metal is having same oxidation state, that is both metals are in +2 oxidation state. Then how we are going to decide which will have greater crystal field splitting is we need to look for number of d-electrons. Here in the case of nickel it is having d8 electrons, whereas in the case of cobalt it is d7. How this number of d-electrons are related to crystal field splitting is they are inversely related. If you increase number of d-electrons, obviously crystal field splitting will decrease. Why it is so? So hypothetically, if you consider the two metals, here the number of electrons are greater, so hence they will shield this metal from approaching ligand. So thereby this ligand is going to have lesser attraction. Since this is an electrostatic attraction, so due to presence of greater number of electrons, so it is going to somewhat shield this metal. Hence this attraction will be decreased, so thereby crystal field splitting will decrease, because so ligand has to approach the metal closer, then only you will have greater splitting, so or else it will not split. So that is the case here. The number of electrons is less, so thereby it is going to shield the metal in lesser extent, so the ligand will approach metal closer, so thereby it is going to split. So this is the case if number of d electrons are greater. So this scenario will be taken only when the metal belongs to same series and they have same oxidation state, or else you can distinguish with the oxidation state itself. There is no need of looking for number of d electrons. When you are going to see the number of d electrons is when they have same oxidation state and a particular given series. Okay, so this is the second, that is number of d electrons, how it is going to affect the crystal field splitting. Now we move on to next, that is nature of metal. Here we are going to consider the principal quantum number. So how this is going to affect the crystal field splitting is, in complexes having the metal cation with same oxidation state, same number of d electrons, the magnitude of crystal field splitting for analogous complex within a given group increases about 30 to 50% from d 3d to 4d, and same amount from 4d to 5d. Here the concept is simple. If you have a metal which is having same oxidation state, and if you calculate number of d electrons, it is also same, then how you are going to decide the magnitude of crystal field splitting is, you need to go for the principal quantum number. So, and as we know, down the group size increases, so the same concept will be applied here. So on moving from 3d to 4d and 4d to 5d, the size of d orbital increases and electron density decreases. Therefore, ligand can approach metal with larger d orbital more closely. So if you look at this hypothetical case, if you see, for example, this is not this is a rough diagram for understanding purpose. Here the electrons are closer, so thereby somewhat there will be some shielding, so the ligand cannot approach. Here the electrons are loosely bound and they are dispersed, so ligand will have lesser shielding, so it can approach metal, so thereby it can increase the crystal field splitting. Here also the same case, the 5d orbitals, the size will increase and electrons are distributed to larger surface, so thereby the ligand can approach easily towards the metal and thereby it is going to increase. Means here there is less steric hindrance around the metal. So this is the example: cobalt, rhodium, iridium. This is triad. So this cobalt belongs to 3d series, rhodium belongs to 4d series, and iridium 5d series. So here you can see it is having same oxidation state, and if you calculate the d electron, they are also same. So where it is differing is principal quantum number. Cobalt belongs to 3d series, rhodium belongs to 4d series, and iridium belongs to 5d series. So thereby it is going to increase the crystal field splitting. So this is how nature of metal ion is going to affect the magnitude of crystal field splitting. Next is spin pairing energy. Metal ion with higher pairing energy will have lower crystal field splitting, whereas metal ion with lower pairing energy will have higher crystal field splitting. So this particular topic I'm going to discuss in detail in the upcoming slides. So for just time being, you just note down that metal ion with higher pairing energy will have lower crystal field splitting, whereas metal ion with lower pairing energy will have higher crystal splitting. So next, if you come for the ligand factor, how the ligands are going to affect the crystal field magnitude of crystal field splitting is here we are going to discuss. So ligands are classified as weak and strong field. So here I think I left with A. So there is some correction, you need to do the correction. It is A, ligands. So here ligands are classified into weak and strong field ligands. So what is this weak and strong field ligands? So ligands which cause small degree of splitting of d orbitals are called weak field ligands, whereas ligand which cause large splitting of d orbitals are called strong field ligands. So this is two types of ligands, that is weak field ligands and strong field ligands. How this has been assigned? It is on the basis of the series called spectrochemical series. So what is that spectrochemical series is? The common ligands have been arranged in order of their increasing crystal field splitting power to cause splitting of d orbitals from study of their effects on spectra of transition metal ion. So this order is usually called as spectrochemical series. Means they are made in series, so depending upon their crystal field splitting power. So that series is called spectrochemical series, and this is the series, and you need to remember this series, and it is very important. So this series will be very useful for determining the electronic transition, magnetic susceptibility, whether decide the complex, whether it is high spin complex or low spin complex. So this series is very useful. So here in the green, I mentioned green color ligands. Actually, SCN, this is also a weak field ligand. So these green colored ligands are weak field ligands, and the ligands which contain oxygen, urea, OH minus, oxalate, oxide ion, water, they will come in the series middle, and nitrogen containing ligands, they are called strong field ligands like NCS, pyridine, ammonia, ethylene diamine, bipyridine, phenanthralene. So those will come as strong field, and carbon containing ligands. Okay, actually this is also nitrogen, it will come under strong field. Carbon containing ligands, they are very strong field ligands. So this is the spectrochemical series. So on the basis of this one, these ligands which is having crystal field splitting power lesser, they are called weak field ligands, whereas carbon containing ligands, they are called very strong field ligands. So if any complex which contains these type of ligands, their splitting pattern will be greater. So it is going to split the d orbitals to greater extent, and if the complex contains this type of ligands, the splitting will be lesser. So you can see the diagram. So if we have weak field ligand, then crystal field splitting will be smaller, and if we have a strong field ligand, and the crystal field splitting will be larger. So this is the ligand factor which is going to affect the crystal field splitting. So once again I will summarize. Ligands which cause small degree of splitting of d orbitals, they are called weak field ligands, and ligands which cause larger splitting of d orbitals, they are called strong field ligands. So this strong field and weak field ligand has been classified on the basis of spectrochemical series. So halogens, you consider halogens, they are weak field, and oxygen containing ligands, they will come in between middle, and nitrogen containing, they are somewhat strong, and carbon containing are very strong field ligands. Okay, and this is how it is going to affect the magnitude of crystal field splitting. Next is number and geometry of the ligands. So already we have discussed different splitting in different geometries. So here how this is going to affect the crystal field splitting. So the magnitude of crystal field splitting increases with increase in number of ligands. Hence, crystal field splitting will follow the order. An octahedral complex has 6 ligands, tetrahedral complex 4, and square planar it is also 4. But why it is having greater crystal field splitting compared to octahedral? And what we are discussing it is number of ligands. If you compare number of ligands in square planar complex it is 4, tetrahedral complex is 4, and octahedral complex is 6. But why this crystal field splitting order is like this is because even though number of ligands in square planar complexes is smaller than octahedral, the magnitude of splitting is greater for square planar complex than octahedral complex because of the fact that square planar complexes are formed by much stronger ligands. So while discussing coordination number 4, we have discussed two types of geometries are possible, that is square planar and tetrahedral. And while discussing in that one, we have classified which type of ligands is going to form square planar is. We mentioned it is strong field ligands usually prefer to form square planar complexes with D8 metal ions. I think you can remember that one. So that is the case. And one more is 2 electrons in the dz square orbitals are stabilized. So here is the crystal field splitting of octahedral and square planar. So if you see the square planar complex, this dz square orbital, its energy is decreased compared to octahedral. So whatever the electron you are going to place, it is stabilized rather compared to octahedral. So these are the two reasons why this crystal field splitting of square planar, even though it is containing lesser number of ligand, because of these two reasons. One is square planar complex, always it is formed by strong field ligands, and one more is 2 electrons in the dz orbitals are stabilized. How it is stabilized? Because of the decrease in the energy of dz square orbital compared to octahedral geometry. Factor which is comes under ligand factor. So that is number of ligands as well as geometry. So this order is completely on the basis of geometry, and if you see the number of ligands, octahedral is having more ligands compared to square planar and tetrahedral. But why this geometry is having greater energy? Already I mentioned the reason. Okay, so these are the factors which is going to affect the magnitude of crystal field splitting. So next task is how to calculate crystal field stabilization energy. We have seen the factors which is going to affect the crystal field splitting. Now our task is to how we are going to find crystal field stabilization energy and what is that crystal field stabilization energy and how we are going to calculate. Now we will see what is crystal field stabilization energy. Crystal field stabilization energy is defined as difference in the energy of electronic configuration in the ligand field to the energy of electronic configuration in isotropic field. So mathematically or in equation wise, if you define crystal field stabilization energy, it is energy in ligand field and energy in isotropic field. What is this isotropic field is? So this is degenerate orbital. So if we have degenerate orbital, then it is going to have certain amount of energy. So that energy is called isotropic field energy. So how we can calculate the energy of isotropic field is, so that is by number of electrons in the degenerate orbital plus pairing energy. So if we calculate or if we find number of electrons in the d orbital and the pairing energy, then we can get the energy of isotropic field. So with this isotropic field, if we minus isotropic field from the energy of ligand field, then whatever the energy decrease in the energy stabilization energy we are going to get, that is called crystal field stabilization energy. So how to calculate this crystal field stabilization energy in octahedral complex? So this is the equation we are going to use for calculation of crystal field stabilization energy, that is minus 0.4 Nt2G plus 0.6 Neg, crystal field splitting in octahedral geometry, plus m into p. So here n represents number of electrons present in T2G and Eg orbital respectively, and m represents number of pair of electrons. And already we have discussed the crystal field splitting that in the octahedral complex the d-orbital is going to split into T2G and Eg. So energy of T2G will be lowered by minus 0.4 and energy will be increased in the case of Eg by 0.6. So by using this crystal field stabilization energy equation, we can calculate the crystal field stabilization energy of octahedral complex. But the question is, how we are going to calculate this pairing energy? We will see. Next is how we can calculate crystal field stabilization energy of tetrahedral complex. So similar to octahedral complex, so the crystal field splitting will be reverse in the case of tetrahedral complex. So the equation will change into crystal field stabilization energy is equal to minus 0.6 Ne plus 0.4 Nt2, crystal field splitting in tetrahedral geometry. Here n represents number of electrons present in E and T2 orbital respectively. But we know that crystal field splitting in tetrahedral geometry is equal to 4 by 9 crystal field splitting in octahedral geometry. So if I substitute these values in this delta T, so I am going to get minus 0.6 Ne plus 0.4 Nt2 into 4 by 9 delta O. So if I simplify this equation, and I am going to get a simplified form of crystal field stabilization energy for tetrahedral complex, that is minus 0.27 Ne plus 0.18 Nt2 multiplied by octahedral crystal field splitting. So we can use either this equation for the calculation of crystal field stabilization energy of tetrahedral complex. If you want in terms of octahedral, then either of these equation, you can use simplified equation or you can just substitute the value and you get the values. So that will give you the crystal field stabilization energy. Next, how one can calculate the crystal field stabilization energy. So here I'm going to take the example of D7 octahedral complex, and here I'm going to find what is the crystal field stabilization energy for a high spin D7 octahedral complex. So D7, since it is an octahedral complex, it will split into T2G and Eg, and the electrons will be arranged like this. So now I need to find the crystal field stabilization energy. So already in the beginning only we have discussed what is crystal field stabilization energy. It is the difference between energy or electronic configuration of ligand field minus energy of electron configuration in isotropic field. So first I'm going to find energy of isotropic field, that is number of electrons present in degenerate orbital, that is 7 electrons, 1 2 3 4 5 6 7. So this is number of electrons present in degenerate orbital and its energy is 0, so there won't be any energy, they are degenerate, so its energy is 0, and it is having 2p, means there are 2 pairs of electrons that will contribute to the energy of isotropic field. So finally the energy of isotropic field will be 2p. Now we need to calculate the energy in the ligand field. since it is an octahedral complex, so we are going to use the formula of crystal field stabilization energy for octahedral complex, that is crystal field stabilization energy is equal to minus 0.4 Nt2G plus 0.6 Neg delta O plus Mp. So by using this formula, so I can substitute minus 0.4 into 5 electrons in the T2G orbital and 2 electrons in the Eg orbital, plus there are 2 pair of electrons. So if we calculate, we are going to get minus 0.8 delta O plus 2p. So finally I need to find crystal field stabilization energy. So how we can find crystal field stabilization energy is energy of electron configuration in ligand field and minus energy of electron configuration in isotropic field. So energy of ligand field, it is minus 0.8 into delta O plus 2p, whereas energy of isotropic field is 2p. So this plus 2p and minus 2p will get cancelled, and I am going to get crystal field stabilization energy equal to minus 0.8 delta O. So that is for high spin D7 octahedral complex. So this is how we are going to calculate CFSE. So what happens if it is in low spin? So what will be the crystal field stabilization energy? So same thing, first we need to find energy of isotropic field. It is same whether it is high spin or low spin, since the orbitals are degenerate. I am going to get energy of isotropic field is equal to 2p. So energy of ligand field, now it will change because it is low spin. So whatever the electron present in the Eg, one electron will come to the T2G level. So here 0.4 into 6, in the previous case it is 5, now it is 6, and plus 0.6 into 1 delta O. Now there are 3 pairs of electrons, so that will contribute to 3 pairing energy. So already I have mentioned MP. M is nothing but number of pair of electrons present in the orbital. Okay, so finally we are going to get minus 1.8 into delta O plus 3p. So finally CFSE, energy of ligand field minus energy of isotropic field. You substitute these two values, minus 1.8 delta O plus 3p minus 2p for isotropic field. So minus 2p and here plus 2p will cancel, and remaining p will remain. So finally crystal field stabilization energy will be minus 1.8 delta O plus p. Okay, so this is the crystal field stabilization energy for low spin D7 octahedral complex. Okay, so this is for high spin. For high spin we have got minus 0.8 delta O. For low spin we got minus 1.8 delta O plus p. So and which one will be preferred? Whether high spin will be preferred or low spin will be preferred, it will be decided by pairing energy. Okay, so what is this pairing energy, how it is calculated? So we will see in the later section. So now for octahedral complex crystal field stabilization energy of Dn configuration. So we have calculated for D7, right? T2G 5 Eg2. So this is high spin and we got minus 0.8 delta O. So if it is low spin, its configuration will be T2G6 and Eg1, and its energy, crystal field stabilization energy, will be minus 1 delta O plus P. So this is two case, high spin, low spin. So and this table has been taken from Inorganic Chemistry by Catherine Housecraft and Sharp, 4th edition. So these are all the different DN configuration. So you can work it out by using the formulas. CFSE you can calculate in the spin. So here there won't be any question of pairing energy. Here T2G1, T2G2 and T2G3. So there is no question whether it is high spin or low spin. So there is no question of pairing energy. Only from D4 to D7 we will have the pairing energy. So we need to consider the pairing energy, and depending upon that pairing energy we can decide whether it is high spin or low spin. So this is for table for crystal field stabilization energy of octahedral complex. So if you come for tetrahedral complex, same, you need to use the crystal field stabilization energy formula whatever we have discussed for tetrahedral complex. From that one we can calculate the crystal field stabilization energy. And one thing you need to keep in mind is for tetrahedral complex we are not at all going to consider pairing energy. Okay, why? Because we will discuss in later. Okay, so this is for tetrahedral complex and this is for octahedral. Octahedral pairing energy will be considered. So when to consider and when it should not be considered we will discuss later. And for tetrahedral complex it is fixed that there we won't consider pairing energy. So what is this pairing energy? So spin pairing energy, that is P represented by P, it is the energy required to put two electrons in the same orbital. So if you take orbital, if you want to place two electrons, you need to have some input energy, you need to give some input of energy, then obviously that electron will get paired according to Hund's rule. So this energy required to put two electrons in the same orbital will be called as spin pairing energy. And this electron pairing energy has two terms, that is one is Coulombic repulsion and loss of exchange energy on pairing. So these are the two terms which is going to contribute to this pairing energy. That is Coulombic repulsion is caused by repulsion of electrons and decreases down the group. So if you are going to place two electrons, there will be, since these electrons are negatively charged, whenever you are going to place in the same orbitals, there will be some Coulombic repulsion. So this Coulombic repulsion has to be overcome by the two electrons so that they can reside in the same orbitals. And Coulombic repulsion contribute to the destabilizing energy. So if the Coulombic repulsion is greater, then it is going to destabilize. Okay, so it is going to contribute for the destabilization energy, and it decreases down the group. So if you go for 4D and 5D, so since the size of the metal increases, the electrons will be, even though you are going to place the electron in the same orbital, they will have minimum Coulombic repulsion. So this is an destabilizing energy, so it is going to add up to the total pairing energy. And one more is loss of exchange energy on pairing. So this contributes to the stabilizing energy associated with two electrons having parallel spin. So mathematically exchange energy can be calculated using the following equation. So that is E exchange is equal to N into N minus 1 divided by 2, where N represents the number of pairs of parallel spin electrons. Okay, so from this equation we can calculate the exchange energy. How to calculate this loss of exchange energy for metal ion? Now, since we are discussing about the coordination complex, so now we need to consider how to calculate the loss of exchange energy. Since it is a stabilizing energy and we need to calculate, and on the basis of this one we are going to have we are going to decide whether we need to add pairing energy to the crystal field stabilization energy or not. That will be decided by the loss of exchange energy. For example, consider Fe2 plus is having D6 configuration and Mn2 plus D5. So in this case, Fe prefers to form low spin complex, whereas Mn prefers to form high spin. And why this Fe prefers low spin whereas Mn prefers high spin. This will be explained by considering the loss of exchange energy. So this is how where we are going to decide whether to include pairing energy or not to include. Already I have shown the table. In the table, so high spin we are not considered the pairing, whereas in the low spin case we are considered pairing energy. So how it is decided will be done or will be decided by this loss of exchange energy and Coulombic interactions. Coulombic it is destabilizing, so we are going to consider stabilizing energy. Okay, so how to find this loss of exchange energy? So we are going to use the formula, that is E exchange, for finding out loss of exchange energy for the metal ion. So now first we will consider the loss of exchange energy for Fe2 plus ion. So Fe2 plus ion, we are going to consider both high spin and low spin as well as degenerate. In the degenerate, it is going to have 6 electrons. In the high spin, it is going to have 6 electrons, but the 2 electrons will be in Eg, whereas in the low spin, all are paired. So for each high spin and low spin, we are going to calculate the exchange energy. From this exchange energy, we are going to find the loss of exchange energy. So use the formula energy of exchange, that is N is equal E exchange is equal to N into N minus 1 by 2. So N is number of number of pairs of parallel spin electrons. So here number of pairs of parallel spin electrons are 1, 2, 3, 4, 5. So these 5 will have parallel spin. So 5 into 5 minus 1 divided by 2. So energy of exchange is 10 here in the case of high spin. So if you calculate for degenerate also, you are going to get 10. Okay. So then come for the low spin. So for this low spin, energy of exchange is calculated by using the same formula, that is 1, 2, 3 number of pairs of electrons with parallel spin. So 1, 2, 3. So 3 into 3 minus 1 by 2. And we need to consider the anti-parallel spin also. So this 1, 2, 3. So I'm going to multiply it by 2. So finally I'm going to get the energy is equal to 6. So how we are going to find loss of exchange energy is by taking the difference between high spin and low spin. So that is energy of exchange in high spin, it is 10, and energy of exchange in low spin is 6. So if I take the difference, it is going to give 4. So that 4 will give you the loss of exchange energy. So this is the loss of exchange energy for Fe2 plus ion, that is equal to 4. Now we need to see for the manganese 2 plus. Okay, here it is having d5 electrons, high spin and low spin. We are going to consider both high spin and low spin. So similarly we are going to calculate the energy of exchange. So number of pair of electrons with parallel spin, 5 electrons. I'm going to get energy of exchange for high spin is equal to 10, and energy of exchange for low spin is equal to 3 plus 1. Here 1, 2, 3. So these are all parallel, and remaining 2 are anti-parallel spins. So 3 into 3 minus 1. So 1, 2, 3 for these 3 electrons, and 2 into 2 minus 1 for these 2 electrons. So finally the energy of exchange for low spin will comes to be 4. So from this energy of exchange we can calculate loss of exchange energy, that is 10 minus 4. So it is going to give 6. So if you compare the loss of exchange energy for Fe2 plus ion, the loss of exchange energy is 4, whereas for Mn2 plus ion, loss of exchange energy is 6. So what conclusion can we arrive at is, from the above calculations reveals that Mn2 plus has greater loss of exchange energy, hence it has higher pairing energy, therefore it prefers to have high spin instead of low spin. So because of higher pairing energy, what this Mn2 plus is going to do is it is going to prefer only high spin instead of low spin. So we can summarize like this. The important result here it is that metal ion will be called low spin if crystal field splitting is greater than pairing energy, and high spin if the crystal field splitting energy is less than pairing. So in this case, loss of exchange energy is greater, so it is directly related to higher pairing energy because this is also the stabilizing energy. So it is having higher pairing energy means it is going to form high spin complex instead of low spin complex. So whereas Fe2 plus it is having uh, lesser pairing energy, so it is going to prefer low spin. So in that case, crystal field stabilization energy will be greater. So that is the case for metal ion. Metal ion, whether it is going to prefer high spin or low spin, will be decided by the pairing energy. So if there is greater loss of exchange energy, then the pairing energy will be greater for metal ion, then it is going to prefer high spin. For a complex, how you are going to decide high spin or low spin? It will be decided on the basis of ligand field strength. So already we have discussed the ligand classification, that is weak field ligands and strong field ligand. So if you have weak field ligands, then the rule of thumb is for weak field ligands, pairing energy will not be considered with crystal field stabilization energy, whereas for strong field ligands, pairing energy will be considered along with the crystal field stabilization energy. So whatever the concept we have discussed above, it is for metal ion. So we have compared with the pairing energy. So now for complex, how we are going to decide whether it is low spin or high spin? It will be decided by weak field and strong field ligands. Okay, so we will see these two by considering example. Okay, so here consider for example two complexes of cobalt. So hexa aqua cobalt and hexacyano cobaltate complexes. Here in the above complexes, we need to decide for which complex we need to add pairing energy along with crystal field stabilization energy. It will be decided by ligand field strength. So in both the complex, cobalt is in +2 oxidation state, hence both will have same pairing energy, hence ligand field strength will be considered. So how this ligand field strength will be considered? Since water will comes under weak field ligand, whereas cyanide will comes under the strong field. So if we calculate the crystal field stabilization energy for both these complex, so for high spin we are not at all going to consider the pairing energy. Why? Because for high spin complex the crystal field splitting will be lesser, so the whatever the pair electron going to pair, it is according to Ohm's rule. So there is no need of input of energy is required for pairing of electrons. Hence for weak field ligand is going to form high spin complex and there is no need to include the pairing energy. So if you come for low spin, here the crystal field splitting will be greater, then there is input of energy is required for pairing of electrons. So hence for low spin complex, if the ligand is strong field ligand, So usually strong field ligand is going to form low spin complexes. We need to add pairing energy. So this is how we are going to decide whether we need to add pairing energy or not. So if we have a weak field ligand, then the complex will be high spin, and whatever the complex it is going to form, it is high spin, and there is no need of adding pairing energy since it is going to obey Hund's rule of maximum multiplicity. So there is no need to put energy for pairing. Automatically it is going to pair because the energy difference is low, so crystal field splitting is low, so electron will be easily get paired. But whereas in the case of strong field ligands, some input energy is required. So in the calculation of crystal field stabilization energy, we need to consider the pairing energy. Okay, so in summary, I given for weak field ligands, pairing energy will not be considered with crystal field stabilization energy. This is very important point you need to remember. You need to, whenever you are going to calculate the crystal field stabilization energy for a particular complex, first and foremost thing what you need to do is you need to check whether the given ligand is weak field or strong field. If it is weak field ligand, so whatever the crystal field stabilization energy you are going to calculate, you need to exclude pairing energy. Okay, and if the ligand is strong field, then it is mandatory that you need to include pairing energy in the crystal field stabilization energy. So that is what is mentioned in the table for calculation of crystal field stabilization energy with pairing energy. So if you consider if it is low spin strong field, whatever the crystal field stabilization energy calculated for D4 to D7 ion, they are included pairing energy, whereas for high spin, that is weak field ligands, there is no pairing energy. The pairing energy has been excluded. So if you consider the D7, so whatever the example if we have taken cobalt, hexa aqua cobalt and hexa cyano cobalt, these two will have D7 electronic configuration, that is 1 2 3 4 5 6 7, 6 plus 7, so D7. So in high spin it is going to have crystal field stabilization energy of minus 0.8, whereas in low spin, if it is a strong field ligand, then the crystal field stabilization energy will be minus 1.8 delta O plus 3p, and it has been clearly mentioned in this table, that is D7. If it is weak field ligand, its crystal field stabilization energy will be minus 0.8. If it is a strong field ligand, its crystal field stabilization energy will be minus 1.8 plus p. Here the pairing energy has been included. So this is how we can calculate the pairing energy. Okay, so these things you need to remember. For low spin complexes, crystal field stabilization energy, if it is greater than pairing energy, then it is called low spin. High spin complex, if you want to call a complex a high spin, then you need to check for whether the crystal field stabilization energy is less than pairing energy. So it is just related to weak field and strong field again. Strong field again, the crystal field stabilization energy will be greater than pairing energy, then it is called low spin complex. And for high spin complex, crystal field stabilization energy will be less than pairing energy. And we have seen for both Metallon as well as for the complex how we can calculate the pairing energy and when to include the pairing energy and when to exclude the pairing energy. Okay, so this is regarding the factors which will affect crystal field splitting, and what is that crystal field stabilization energy, how to calculate the crystal field stabilization energy for octahedral complex as well as tetrahedral complex, and in which case we need to include pairing energy and in which case we need to exclude pairing energy. So I will stop at this stage. Thank you. Stay safe, stay at home.